Before we look at the parallel axis theorem, I just want to mention an important point about the center of gravity of a body, or the center of mass. Let's suppose that this is some lamina. Now it doesn't have to be uniform, it could be non-uniform. Indeed, it doesn't have to be a lamina, it could be some three-dimensional object. In that case, we would have x, y and z coordinates. But just to keep things simple, we will just assume that we have a two-dimensional object that doesn't necessarily have to be uniform. It could be non-uniform, so the density over here, say, could be greater than the density here. Well, since it's a lamina, we can ignore the thickness of it, so we just have two dimensions to consider, x and y. We know from previous videos that the coordinates of the center of mass are given by this formula here, where each little mi is a mass element. Now I could write delta mi for each mass element. That probably would be a better notation, but I haven't actually shown the deltas here. Mi times xi is the moment of each mass element about the x-axis. So if this is a mass element, you can call it delta mi or just mi, then its moment about the x-axis is got by multiplying its mass by yi actually. This is actually this here, sorry. This is the moment of it, a mass element about the x-axis. If we want its moment about the y-axis, we multiply its mass by xi. That gives us this here. And we have to take the sum of all such moments for each mass element, for all the mass elements that make up this body. And we must divide by the total mass of the body. That's the sum of all the mass elements that make it up. We can call that big M if you like. So anyway, if we do that, we have the center of mass or gravity of the body. Now, imagine if our xy axes are moved so that the origin is at the center of gravity. Now we could still perform this calculation, of course, but each xi would be different, so the position of this mass element is now different than it was when referring to our original axes, and also yi will be different. But of course, if we perform these calculations, we'll have to get 0, because the center of mass is now at 0. So when we calculate this thing here, we'll get 0, and that makes sense because some mass elements have positive x values and some mass elements will have negative x values, and they'll all tend to cancel each other out. That's actually the definition of the center of gravity. We could define the center of gravity this way, by saying the sum of the moments of all mass elements about the center of gravity is 0. I keep saying center of gravity. Well, we can use center of gravity and center of mass interchangeably here for objects near the surface of the Earth, because the weight of the object is just the mass times g, the mass times a constant. So anyway, if this quantity is 0, well, obviously the sum of all the moments, as I just said, about the y-axis is 0, because this must be 0, because underneath is not 0. The total mass is certainly not 0, so we need the numerator to be 0. Similarly here, the sum of all the moments of the mass elements about the x-axis is 0. Now let's take any body. It doesn't have to be two-dimensional, it could actually be three-dimensional, but to keep things simple, we'll just pretend it's two-dimensional. Little c is the center of mass of this body. Big C is an axis passing through the center of mass. Let big I sub c be the moment of inertia of the body about this axis, big C. Let's consider another axis L, where L is parallel to C. Big I sub L is the moment of inertia of the body about this new axis L. The parallel axis theorem tells us that the moment of inertia of the body about any axis, well, let's say about axis L, is equal to the moment of inertia about a parallel axis through the center of mass, plus the mass of the body times the square of the distance between the two axes. So let's see what this says. The moment of inertia of the body about any axis, let's say this axis L, is equal to the moment of inertia about a parallel axis through the center of mass. Well, that's just IC plus the mass of the body. Let's suppose the mass of the body is big M times the square of the distance between them. Let the distance between them be d. To prove this, let's take a mass element delta m and get its moment of inertia about both of these axes. Let's suppose the perpendicular distance of this mass element to the axis through the center of mass is r. So remember, to get the moment of inertia of a mass element about an axis, we must multiply its mass delta m by the perpendicular distance squared of it to the axis. We are interested in the moment of inertia of the object about axis L, so we need the perpendicular distance of the mass element to this axis L. Well, that's just r minus d, where d is the perpendicular distance between the two axes L and C. Now, to get IL, we have to take all such mass elements and get the sum of their moments of inertia about axis L. So we multiply the mass by the distance of it from the axis squared. Actually, to be more precise, we have to take the limit as delta m goes to 0. So this summation becomes an integral. Now we can expand out this bracket, so we have r squared minus 2rd plus d squared. We can multiply delta m into each of these terms, and we're summing this expression, but we can just sum each of these terms. We can sum this term separately from this one, and we can just take those three sums. Here we have sigma delta m of r squared times r squared. Well, that's just the moment of inertia of the mass element delta m about axis C. It's a distance r from C. So, when we take the sum of all those mass elements and take this limit, this term here is just IC. Now, what about the next term? Well, the 2d is just a constant. We can take that outside the summation sign, or the minus 2d, and we have to sum delta m times r. But from what I said at the very start of this video, this is just the sum of the moments of each mass element about an axis that passes through the center of mass C. So our origin is actually located at C. So this is the x-axis, this is the y-axis, and we know that if we sum all the moments of mass elements about the center of mass, we get 0. If we put a coordinate system here, the center of mass is now 0, 0. That's just the definition of the center of mass. It is a point in the object such that the sum of all the moments of the mass elements about that point are 0. So that term is just 0. And finally, we have delta m times d squared, and we want to take that sum, but d squared is just a constant. It's just the distance between the two axes, so we can pull that out and just sum all the mass elements. But the sum of all the mass elements is just the total mass of the object, which is m. So that's the proof of our result. I sub L equals I sub C plus md squared. Now, in the previous video, we calculated the moment of inertia of a uniform tin rod about one end of the rod and also about the center of the rod, and we are going to see that the parallel axis theorem does indeed give us the results that we got. So the center of the mass of the rod is located at the center, the geometrical center of the rod, because it's a uniform rod. So we will consider the moment of inertia of the rod about this axis. Well, that's IC, and we'll also get IL, the moment of inertia of the rod about one end of the rod, and we'll show that this relation holds. So L is this axis here about the end of the rod. D is the distance between the two axes, as we saw in the theorem. So IL about the end is ml cubed over 3 IC. Moment of inertia about the center of the rod is ml squared over 12. This here is ml squared, and then we have the mass of the rod times d squared. Well, what's the distance between these two axes? Well, the distance is just half the length of the rod. Now this term here is going to be ml squared over 4, and if we multiply above and below by 3, that's 3ml squared over 12. So 3/12 is the same as a quarter, and if we add these two together, you see we get 4ml squared over 12, and that's just ml squared over 3, same as this here. So this does check out.